Welcome to the workshop on diffusion models for molecule generation. This one is going to be hosted by Chin-Wei and I. We both come also from Microsoft Research in Amsterdam, AI for Science, and we work together with Rianne, who presented the session in the morning. And this session is divided in two main parts. First is a quick paper presentation on equivariant diffusion for molecule generation in 3D. It's basically a diffusion model to generate molecules. And the second part, the longest one, is going to be the workshop, where we will learn how to code this diffusion model for an easy toy example and also for molecular data. So yes, let's start with the paper presentation. We will present the equivariant diffusion for molecule generation in 3D. This is a paper I did during the PhD in collaboration and equal contribution with Emil Hugeboom and Clement Vignac, and supervised by Max Welling. The paper was done at the University of Amsterdam in collaboration with the EPFL. And basically, the paper is organized in the following sections. Well, the presentation, I will start introducing a motivation on why to generate molecules, then some background on denoising diffusion and equivariant graph neural networks, and then we will use these two concepts from the background to define how the equivariant diffusion model is defined. So yes, why to generate molecules? Why is this like an interesting thing to do? So basically, some of the main applications where molecule generation can be applied, some of the main domains is drug discovery, catalyst design, material discovery, docking problems. All of these domains, they have been addressed in the past with, well, some more classical techniques and also some more basic machine learning techniques, but there is the chance of a transformation similar, like the same that deep learning has been applied to computer vision and natural language processing. There is also now the potential to transform the molecular modeling field, also with deep learning techniques, and that can be leveraged into all these domains like drug discovery, all these nice applications we see. This is also why there is now so much investment, so many companies, as for example, like in our case, working in Microsoft, working on this research of deep learning for molecular modeling. So yes, the concepts that we need in order to understand the equivariant diffusion model, we're going to introduce the two concepts necessary. One is denoising diffusion, which was already explained by Rianne in the morning, so this is just a quick recapitulation of that. So basically, denoising diffusion is a generative model that consists on two processes, a diffusion process and a denoising process. The diffusion process basically takes a sample from a data distribution, and then it diffuses it into a Gaussian distribution. Then we can compute the reverse process, denoising. That's going to be the generative process, for which we sample from this Gaussian distribution into the data distribution. By learning this denoising process, then we can just sample Gaussian noise, and then by doing this reverse process, this denoising process, we can obtain samples from the data distribution from which we are training on. So probably you have all of this. You have seen all of this in internet, like all of these image generation, like DALI and stable diffusion. These algorithms are using diffusion models, and yeah, now they are becoming very popular in image generation. The goal is also to apply it for molecular modeling. The progress is not as fast as in image, but there is the potential to also have very nice applications in molecular modeling as it's happening in images. Another basic concept that we have to introduce before we explain the equivariant diffusion model is the concept of equivariance or invariance. This is actually a very intuitive concept. Sometimes can be explained with more complicated math, but the intuition behind it is very simple. And it's basically about leveraging symmetries on the data. So, for example, when we learn a function to predict the energy of a molecule, we know that the energy of a molecule is invariant to orientations or translations in this molecule. Therefore, the function that we want to learn, we want it to be invariant to those rotations and translations. So we want to impose those constraints into the neural network. And so here we just see like an example of, we just have a molecule, and then the energy that we will obtain at the output it will be invariant to rotations or translations in this molecule. So we want the function to be an invariant function to those transformations. The concept of equivariance is very similar. The only difference is instead of invariant, we want the equivalent transformation in the output. This is also something like, for example, when we apply forces into a molecule, the forces are equivariant to rotations. So it means that if we rotate the molecule, the forces that we will compute will be also rotated at the output of the function. Technically, we can define equivariance such that if we have a function and then we have a transformation, we obtain the same result if first we apply the function to the sample that we have, and then the transformation, it ends up in the same than if first we apply the transformation and then the function. So this is just a basic diagram here. We see that if we first apply a function, in this case the equivariant graph neural network, into the top left sample, then we just obtain a transformed sample, and then if we rotate it, we will obtain exactly the same than if first we rotate it, and then we apply the transformation. That's the property of the EGNN of being equivariant to rotations or translations. This concept that we are leveraging for this molecular modeling is something that has already been used, even if maybe at the moment the CNNs were designed, the term equivariance was not used, but convolutional neural networks are equivariant to translations. That's why they can scale to these high-dimensional inputs, which with just a standard multi-layer perceptron, it was impossible. So basically what we see here is that if we have an MNIST digit that we want to classify, this is the convolutional neural network used in the Khan paper in the 90s, I think it was, then the output should be invariant to translations of this representation of this zero we have in the image. Additionally, the layers in between are equivariant, so it means that if we translate equivariant to translation, so if we translate the input, the output translates. This is a property of convolutional neural networks. In the case of molecules, we're interested in the following symmetries: translations to three-dimensional space, rotations, and permutations. The translations and rotations, we call it E3 equivariance when we also include the reflections. Otherwise, we will call it SE3. And then permutations, this is a concept for graph structure data or point clouds. So it basically means that when we, for example, represent a molecule as a tensor with a set of points that represent the coordinates and some atom features, if we permute those representations in our tensor, we will still have the same molecule. That's why we want to be permutation invariant or equivariant. So basically, since these are the three symmetries that we are interested when working with this generative model for molecules, we use a neural network that is E3 equivariance, and it's also permutation equivariance. So this is the EN equivariant graph neural network. There are many neural networks to achieve this, that satisfy these three symmetries. This is a very simple solution that works well enough. There are some now that work better, but also in a trade-off of efficiency. This is a work that we did with some of the same authors of this diffusion paper, and this is the network that we are going to use to define this equivariant diffusion model in the paper and also in the workshop later. But yes, basically we don't really need to dig into this. At least in the workshop, we'll just import the neural network, and this will be just replacing what will be the neural network used in the diffusion model. So basically, this is what the equivariant diffusion model is doing. So we just sample a bunch of Gaussian. We have a set of points, and then we just sample them from a Gaussian distribution. Then we apply this denoising process that is going to generate these molecules and we train this process from molecule data set. In particular, we are going to train with QM9. This one we see here is GeoMDRAGs, which is for bigger molecules. We're going to work in the workshop with smaller molecules than these ones. But basically, this will be the concept. So we start from Gaussian noise, and then it generates a molecule by denoising this Gaussian representation. This paper was when presented, was closely related to previous papers. One was GeoDiff, which was using equivariant diffusion not to generate molecules, but to generate the coordinates of a molecule. So given the graph of a molecule, we could generate its position in 3D space, which was also using the EN equivariant graph neural network. And a previous work that was doing the same application than this diffusion model was equivariant normalizing flows. This is a paper we did with the same authors than this diffusion model. So basically it follows the same principles, but the diffusion models seem to give better performance than normalizing flows. Even if now there are some papers that are still like improving normalizing flows, so let's see in the future what ends up working better. But right now, the state of the art seems to be in diffusion models. Okay, so this is the model that we're presenting. Basically, we have this molecule representation, and then we learn a diffusion process that destroys information in the molecule. Then we learn the denoising process to generate the molecule from noise. And this process, it handles the continuous and discrete data in terms that we have the molecule represented as atom coordinates, the positions of the atoms, and then we also have discrete data as the label of the atom, like if the atom is a carbon, oxygen, hydrogen, nitrogen atom. So we are diffusing and denoising these two types of data together. We represent the coordinates as X and the atom types as H. So the diffusion process is built in the following way, as you can see in the image. We just take a sample, and then there are like all these steps where a very small amount of noise is added in every time step until it results into a Gaussian distribution. There is this property of Gaussian distributions that if adding Gaussian noise many times, we just end up with a Gaussian noise of a higher variance. So this implies that we can just sample at any time step, but just picking the variance of the Gaussian distribution. So given the sample, when we want given the sample from our data set, when we want to sample a diffuse representation, we can sample any intermediate time step. This is not the case at denoising. We're going to do step by step at denoising, but at diffusing, we can sample any intermediate representation, and this is going to be very useful at training. But this is something, a property from diffusion models. Thus, it's not specific for molecules.
Sorry?
Yes?
Question here. So the molecule is not represented as a graph, but pure XYZ position and the molecule type.
Yeah, exactly.
Okay, so you don't know if there are chemical bonds between the molecules?
Yes, so the molecule is represented as a point cloud. So it's basically the X coordinates and the atom types. And then when plotting this, in the bond information is just obtained from this representation. So given a pair of atom types and the distance between them, we assume if there is a bond or not. Like we just use some of the commonest, like the average bond distance that you will find in a table in chemistry between, like, for example, carbon and hydrogen bond. What's the average distance? What's the standard deviation? We use those metrics then to plot what you see here, the bonds between atoms. But the neural network, it only models point clouds. It doesn't model we don't input this edge information, but it's kind of what you see here, it's intrinsic in the point cloud, even if it's not explicitly passed to the neural network. But by the way, if there is any question, just feel free to interrupt. Yeah. Yes. So do you mean maybe for the molecules as molecular data, or maybe specifically for this diffusion model? Okay. So yes, so the relation of, okay, we have the concept of invariant and equivariance. And then invariance basically means that if we apply a transformation, we have a function that then if we apply a transformation to the input of this function, we want the output to be invariant, so we don't want the output to change. This is something that is very useful in tasks like, for example, when you want to obtain the property, like if you want to do molecular property prediction, the property of a molecule doesn't change depending on the translation and orientation. So, yeah, for example, if you want to compute the polarizability of molecules, that's independent from the orientation or translation of the molecule. Therefore, you want to design let's say, your neural network, what you're using to predict that. It's nice if it's invariant, because then if you give it in a different orientation, it's not going to change the output, which it should not. Equivariance, it means that the output is going to change with the input in an equivalent way. So that means that, for example, your output, imagine you are you're predicting the forces of a molecule given the molecule conformation. You want to obtain what are the forces on that structure. Those forces is a set of vectors in every node that is pushing the node into a direction. So then if you rotate the molecule at the input, like you just apply a rotation matrix to it, you want the forces at the output of this function to rotate with exactly in the same way. So you could just, let me see the equation here. So here you see that you can have this rotation matrix. Imagine X are the positions of the molecule. Then if you apply this rotation operation on this sample, okay, yes. So yeah, if we apply this rotation operator to the molecule, then we expect the forces to rotate exactly in the same way.
That's the part that confused me. Even if it's rotating, it's still the same. Or it doesn't change. Like the properties shouldn't change.
Can you repeat the last part?
I think that's the part that confused me. That even if you have like the forces applied to the molecule and it's rotating in an equal fashion as proportional to the forces that are being applied,
Yeah.
the molecule itself remains the same, right? It doesn't change the properties of the molecule or anything else, or does it?
So let me see so the properties of the molecule are the same, but I mean, let's say of the molecule you input are the same. So if you have this molecule at the input of your network, the properties are the same when you translate or rotate it. And then the forces are going to rotate with rotations of the input, but the properties on that molecule at the input are going to be the same. So the molecule is still going to be invariant to some properties, like energy or polarizability, but the output is going to rotate if you predict the forces.
So there are some things that stay invariant.
Yes. So
Some things that are
yeah, exactly. So there are some properties that are intrinsically invariant and others that are equivariant. Then you can choose the architecture one way or the other. Yeah. Okay. Okay. So yes, we were describing the diffusion process, and now we want to describe the reverse process that we use to generate molecules, the denoising process. Basically, the denoising process, and when we have access, imagine we have access to the protein that we will be, to the molecule that we will be generating. This denoising process could, like the distribution that defines it, could be, like we could define the true denoising process, and it will follow also Gaussian distribution. When we generate, of course, we don't have access to the sample we're generating. So then, in order to obtain this, like to compute this denoising process, what we do is we estimate the mean of this Gaussian distribution. So basically, the denoising process is just going to be also Gaussian, like Gaussian distributions at conditional Gaussians at every time step, for which we are going to estimate the mean of this distribution. It's going to shift the mean of this distribution towards the sample that we are generating. So yes, basically just like the denoising process. We have some noise, and at every time step, we have a Gaussian distribution that shifts the mean towards the distribution that we are generating. Yes?
I have understood what's the definition of
Can you repeat a bit louder?
The H random variable. What does it define? To go back.
So there is no. So what do you mean by edge random variable? So we are. So we are not defining edges. We're defining just the point cloud. H. Okay, sorry. Yeah. Yes, so H defines the atom types, X defines the positions.
Okay. And I haven't understood how you invented this kind of property of equivariant and invariant in your model.
Yes, so the equivariance is going to come from the way we're going to, so later, I mean, it's going to come later in the slides, but just to give you an update before that. Is just gonna be, so we're gonna use an equivariant graph neural network in order to model this mean that we are gonna estimate here. So when we compute this reverse process, we are gonna estimate the mean of this reverse process, and we are gonna do that with a neural network that's gonna be an equivariant neural network. And that makes the whole process, the distribution, like the probability of the whole process is gonna be equivariant because, just all the individual ones are going to be modeled by this equivariant network.
Sorry, another question. But the diffusion process only acts on X or also on H? Because H is free.
Yes, it acts on both of them. That's actually a good question. So it acts on both of them. There are on H and X. In X is quite trivial, right? It's a continuous space. We can just diffuse it. On H, there are different works also that diffuse on discrete data. When building this model, we also tried some option. Well, we tried actually, some. I think it was called the Armax flow. So we will map at the beginning the H to a continuous space, and then we will diffuse in that continuous space. In the end, we got better performance by just diffusing directly on the discrete space. So you can interpret that as, imagine you have your discrete space, and then in the first time step, you add some Gaussian noise, and that maps the discrete space to a continuous space, which is a Gaussian distribution with a small variance, and then from that, we just continue diffusing into the Gaussian distribution. So basically, we just add the Gaussian distribution into the discrete space, and that gave better solutions for this model than trying to use some methods that will map it to continuous, like with, for example, with a normalizing flow, and then diffusing the continuous space. That gave better. So it's nice because it makes the solution simpler. I wanted to say something about that. Well, there is a slide later. I'm gonna go a bit deeper on that. On also some trick to make it work better. Okay, so then the optimization process. How does it go? So basically, we just have this sample that is represented with X and H. So the sample is basically X is the continuous data, H is the discrete one. So we sample a diffuse, we obtain a diffuse sample of this molecule. Feel free to ask, Anna.
What happens when the label diffuses outside of the support of your discrete space? You add a Gaussian noise and you have label 1, 2, 3, 4, 5, or whatever.
Yes. So it's just, so let's say that the labels are 0 or 1. It's a one-hot encoding. And then when we diffuse it, the diffusion is going to go something that, Gaussian distribution around 0, right? So it's going to go from a minus to a positive value. It's just, so there is nothing wrong with that. In the end, when we map back to the continuous space, so the network is going to push things, again, towards 0 or 1. And let's say if you have a one-hot encoding, what you want then is just to obtain which one gives you the maximum value. And then you just compute the Rmax of that, and that's going to give you the label of the atom. So it doesn't matter if it's in the, if it gives something like -1 or farther than 1, you're just going to take whatever it's closer to the 1 value. The others are going to be closer to 0. And and that's going to be, I would say it's similar when you do like image classification, and then you have some yeah, you obtain some continuous, like your labels, like are a continuous value, but in the end you do an argmax, right, of the continuous value you obtain, and that's going to tell you what is the label of that image. It's similar here. You just obtain some continuous values, and then you just do the argmax, and that's the moment you map it back to discrete, and it tells you the label. Yeah. Yeah, exactly. Yes. Thank you, Rianne. Okay, so yeah, now that we got this working, so we have the way we optimize, we train this network is we have our sample, then we add some noise to it. Basically, sampling from this distribution, like from this diffusion distribution, is just as we just take a sample, and then we do a weighted sum of these samples with some noise, and then the amount of noise we put is going to be given by the variance of the noise distribution that we can see here, which is indexed by the time step, which it's just like larger variance for those values that are in larger time steps, and smaller ones for the ones that are closer. So basically, we just take the sample, we add some noise, we get this diffuse sample. Then we are going to have a neural network, the equivariant graph neural network, that is going to estimate, given this noisy sample, it's going to estimate which is the noise that was added to this sample. So the target is just going to be the noise that we added, then we input this diffuse sample, and then the network has to estimate in this sample what is the noise that was added to it. This is basically the optimization loss. So it's actually pretty simple, even if there may be questions to get to it. They're a bit more complicated. This one is the optimization loss. It results in something very simple. And then this is this network that we are going to use this one to reparameterize the denoising distribution. So we saw that the denoising distribution was a Gaussian distribution, and then that we had to reparameterize the mean of this Gaussian. So basically, this network that it's learning how to remove noise, so it's predicting noise from the sample, so we will use this noise to remove it by parameterizing this denoising distribution with this neural network. So basically, the denoising distribution, the only learnable parameters are in this neural network, and then it's just parameterized by this. Yeah. Yeah, it's a graph convolutional. It's equivariant graph neural network, so it's graph convolutional. We use a fully connected message passing setting, so it means that each node is going to get neighbors it's going to receive messages from the other nodes. And yes, and then the main difference of the equivariant graph neural network with the standard one is that instead of just having the features, like in a standard one, you will just have, let's say, H features, the features that we have here that we call H. Then it applies the standard equations you will have in a graph neural network. The equivariant one has an extra update that it also updates. Let's say it's an extra update that is equivariant. It's assigned to be equivariant. And it also updates using the weights learned by this graph neural network. It also updates these equivariant features, which are the coordinates, using an equivariant update. Yes, so it's basically a standard graph neural network as the one that you were asking, with this extra equivariant update. Okay, so yes, how do we deal with the discrete data? So yeah, we opted for this very simple solution, which is just concatenating the continuous and the discrete data, and then we just diffuse everything together. Yes, one thing I wanted to add before I forgot to say is that this is something that kind of works well in low-dimensional spaces. In QM9 or geom drags, I think in QM9 we have 5 atom types. In geom drags, maybe we had something like 20-something atom types. Those low-dimensional spaces are good enough to just apply the diffusion and denoising process directly on this, what was like this one-hot encoding, and still obtain very good results, and then it simplifies a lot the model. So basically, here we can just depict how. So basically, it will be like one hot will be like a delta. Then when we add just some noise, we start diffusing these delta peaks. Like for example, if If an atom is labeled as 1 or as 0, we will obtain in the first diffusion step something like this. And then as we go towards the diffusion model, both Gaussians are going to converge to a Gaussian with unit variance at 0. And then when we adjust the noise, we're going to just obtain something like this. And then here I think is what you were asking. We're just going to say, okay, if in that one hot encoding, that particular atom is closer to 1, we're just going to pick that one. We're going to do the argmax and pick that atom type. If we have values that are negative, it just doesn't matter. We just pick the biggest one. It's a bit of a trick, but in practice, it worked very well. That's why we used it. One thing that we also realize is that if we set this diffusion, like this one hot encoding to 1, or we set the number to something smaller, like for example, imagine we have a one hot encoding where everything is 0 or 1. Imagine we have a one hot encoding where we make the 1 smaller, like imagine everything is at 0 or at 0.25. Then if we make this smaller, the diffusion process is going to merge things quicker. So the denoising process is going to decide which atom type it is more towards the end of the generative process. So by tuning what magnitude we give into this one hot encoding, we're choosing when in the denoising process are we picking the atoms with respect to the positions. If we make it smaller, the atom types are going to be selected more towards the end. This is like a small detail, but it really changed in performance. So when we compute the molecular stability just by adding, like by making this one hot encoding a bit smaller, we will map the molecular stability, a metric we're using, from 47% to 82%. And then some posterior works also have shown that it's more beneficial to choose the atom types towards the end of the generative process instead of towards the very beginning when doing molecule generation. So just a small detail, but I think it's worth it mentioning it because the change in performance was quite big by just doing this small thing here. So here are some of the results. Basically, yes, we have two rows here. We have the QM9 and GM-DRAX. We have two baselines that we were comparing. Equivariant normalizing flows is the first one, a previous paper that's using the same network but normalizing flows. Then this GISHNet, if I remember well, I think this was an autoregressive model. And then we had the GDM and GDM augmentation. Those were our two baselines, which it's basically the same exact model, but instead of using the equivariant graph neural network, we were using the same network not being equivariant. As you can see, the performance is also good, but a bit worse because it takes longer to train. Basically, the GDM augmentation is the same network, not equivariant, but doing data augmentation. So we input also the samples rotated, so it learns the symmetry. Instead of enforcing the symmetry, we learn it. Yes, performance is also quite good, but a bit lower than using the equivariant graph neural network. And yes, the results were quite surprising in terms that it worked pretty well compared to the previous works in molecule generation with deep learning. And yes, and then this, just analyze for QM9, GM-DRAX, the atom, we predict here the atom stability and molecular stability. These are some heuristics, so it's like a metric that we use, like atom stability. Basically, it checks if the valence of the bond is equal to the sum of the bonds of that atom. So basically, for example, in a hydrogen atom, you have valence 1, so you will expect it to have 1 bond. Then we say it's stable. If you have a hydrogen atom with 2 bonds, that should not happen in reality, so we say it's unstable. If it has 0 bonds, we also say it's unstable. We do the same with carbon. It should have 4 bonds. Oxygen, it should have 2 bonds. So we just check if the bonds of these samples are realistic. We see in the data for QM9 in this particular data set, we got like 99% and 95.2%. And then the methods, usually the better performance they had, the more they got closer to it. Of course, there are other metrics in the paper. I didn't add them here, but such as novelty or uniqueness because you could just predict everything is stable if you just predict the same molecule the whole time and it's correct. You also want some novelty and uniqueness. Those are also in the paper. The numbers were also very good. I just didn't add them for the space here. And another experiment we did about this method is to make it conditional. So basically, we want to condition generation in a property. Like, for example, the one here in the slide is polarizability. And this is very simple. So we can just add the conditioning of the molecule by conditioning the network into. So as you can see, I just added a C here. This is the property. So basically, when we train, we input into the network the property of the sample. And then, since we are learning to denoise it, a generation is going to learn that for this property, like for example, if we have a network with high polarizability, and then we are here introducing the polarizability value. Later, when we generate, if we introduce again a large polarizability value, it's going to generate molecules with large polarizability values. So basically, this is the only change we need to do with conditional, just to input the property we are conditioning on. The diffusion process is still the same because we are not diffusing the property, just the atom types and the coordinates. That's just something we condition on. And these are some generations in QM9 based on the property polarizability. So we show that we show how the molecules look as we increase this property. This is for a fixed random seed. We just sweep over the property value. For large polarizability values, we will expect like longer molecules. Also, the distribution of atoms, for example, you will expect something like oxygen to be in one side because it's also like polarizing it more than if you only have carbons. So you can see that this is something that is happening here. As we increase this polarizability value, we see that the molecules get a bit longer. In the one with maximum value, we see there is an oxygen atom at the end, which is also like pulling more the electrons. So this is just like the experiment in conditional. Maybe the results we got with these are not as good enough to just say we want this molecule, given these properties, just generate this. It would be ideal if we will be like we want to design a drug or some type of molecule, and then we are just, okay, these are the properties we want, please generate it. It doesn't work that well, but it's just like a step towards that direction in terms that it respects what we are inputting, and it generates something that is consistent with the input. Okay, so yes, basically that was the presentation of the diffusion model. So basically the conclusions are that diffusion models in the literature have demonstrated outstanding performance in many tasks, especially like computer vision and then this, let's say that all this benefit like is still, it can be brought to molecular modeling. They are also giving some of the best performances in molecule generation. And there is still a lot to improve there compared to other fields. It's a very exciting line of research, and there are many applications that can benefit from this, like molecular dynamics, or just like drug discovery, or many applications in chemistry that can benefit from this type of research. So then the next is going to be the workshop where we will show how to code this equivariant diffusion model. It's going to work for a toy experiment and also for molecular data. We are going to have a small QM9 partition for the molecular data. So basically, this will just be a very quick overview. So basically, we're going to code a model that has some Gaussian noise, and then it can generate this. The first one is the toy experiment. So when we sample Gaussian distribution, then we can map it back to the 2 moons distribution. That's toy experiment, and then we can also do the same for QM9. Chin-Wei is gonna continue, and then he's gonna introduce the workshop and the collab, how to set it up. Break. Oh yeah. Okay. Yeah. So before that, we'll just do a quick break. And then Chin-Wei will continue with the collab session. Thank you.
All right. So if you click on the link, it's gonna bring you to a collab notebook, and the first thing you're gonna do is just to create a copy, just locally in your drive. So you can just select File and go down to save a copy in Drive. That way you wouldn't, yeah, the thing that you edited will be saved. Okay, and once you created a copy, you can follow the instruction, the first 2 steps. So if you want to use the GPU, that's a good thing. You can select runtime and change runtime type, and then you can select a GPU. And once that's done, we're going to install some dependencies. So first, we're going to clone a GitHub repository that we're going to be using for this course. And then install a library that we're going to be using. Is there any problem with installation, cloning? All right. So give it some time to install. I'm going to walk you through the code quickly. If you click on this folder on the left here, it's files. You can go to the ProbAI, which is the folder, the repository that you just cloned. And for the first part of this session, we're going to be using one file in the source folder, models, the ddpm.py. So if you double click it. So this is the main file that we're going to be using for this session. All right, everyone's with me? Cool. Okay, so in this file, there's a ddpm class. We're going to be implementing some of the core functions for diffusion model. So first of all, as Rianne and Victor went over the materials earlier today, we already know what a diffusion process is and how we're going to denoise the process to generate the data. So we're going to start with the noise schedule, which is the beta coefficients, and its business with the other coefficients that depends on it. So we're going to start with maybe just a very simple example of a noise schedule, which is going to be starting from a it's going to be a linear schedule between a small value, like 0.0001, and a large-ish value, 0.02. And we're going to linearly interpolate between these 2 values. And that's what that will be implemented in this get coefficient function. Okay? And before we start, maybe I can just walk through this module real quickly. So in the DDM class, first of all, we are going to instantiate the class by calling this get coefficient function, and you're going to implement this yourself. There are 2 types. One is the linear schedule. The other one is cosine schedule. The formulas will be provided here. And once that's done, you have an instantiation of a DDM class. And for training, we have a loss function, which is here, which will do all the sampling and the passing the noisy sample to the model for you and calculate the loss. And in order to obtain the noisy sample, you're going to perturb the original data through the versional queue process, right? And the queue will be defined here. We're going to parameterize the mean and standard deviation as a function of time. And this is also something you're going to be implementing. And then once you obtain a sample of your noisy data now, we can pass that to our model, and then we have a prediction of the noise, right? And then we can use that as we can calculate our loss by comparing our prediction of the noise and the original noise. Okay, and that's pretty much all there is for training. And at the end, once the model is trained, for the sampling part, we're gonna have some sampling code here, which we'll call the mean and standard deviation for the reverse process for generation, the p of xt minus 1 given xt. And you're also going to implement the mean and standard deviation for this function yourself. Okay, so just a quick overview. All All right, so let's get back to our first task here, which is implementing the get coefficient function. So we're going to start with a linear noise schedule, which is interpolation between small beta and large beta coefficients. And once you are done, okay, let me expand it. Once you are done, you can run this PyTest to see whether your implementation is correct by comparing with the ground truth. So now, if you have already implemented the linear schedule, let's move on to the next task. So given these coefficients, we can now parameterize the marginal distribution at time step t that you're going to be using to inject noise to your original raw data. So in the lecture, we already see that after you define the Markov process, right, you have this noisy diffusion process. You can marginalize out all of the intermediate layers, and you can obtain this formula for ZT given Z0, okay? And the formula is given here, which is a Gaussian distribution depending on your data, which is Z0. And the mean and the variance of this distribution is as written here. So the second task here is to implement the mean and the standard deviation of this Gaussian, which will be the Q mean and Q STD here. And after you're done, you can run a test to see whether your implementation is correct. You have to be careful here to make sure the shapes of the thing is the same as your data. So once you're done with that, right? So we define how to sample from this distribution in this handy function called QSample. So once you implemented the Q mean, Q standard deviation, then given for each row of the data, right? We can sample a different time step. We will get the mean and standard deviation, and then we can use the parameterization trick here to sample ZT. So we simply just multiply, a independent standard Gaussian noise by this standard deviation and plus the mean. And that's how you sample from this distribution, okay? And once that's done, we can go through how training is done. So training is done by first sampling a discrete time step, and then sample this ZT according to this time step. And then we pass it through the model. We predict the epsilon. And then we're going to compare our prediction with the actual noise. And that will be implemented by this underscore losses function. So you're going to be doing that in this function. And here you simply just need to implement the sum of square error, so summation over the feature dimensions. And that's it. And you can quickly test that to see if your implementation is correct. Hello. So I'm just going to tell you the next task, because some people are already there. And you can also take a break if you want, meanwhile. So the last task, once you train your model, right, so you are able to sample from this noisy distribution and then make a prediction about the noise, and you can compute the loss, and then you can actually start training now if everything is implemented correctly. And now, in order to see whether your model is working, you want to see whether you can generate stuff. And to do that, you have to implement the sampling part of the diffusion model. So here we already implemented a loop for you. If you want to go through that, that will help you understand a bit more how it works, right? So this iterative process for n steps. And so the next task here is to implement the mean and standard deviation of the reverse process of this P of Z t minus 1 given ZT. And that should be somewhere down there. For some reason, I'm disconnected. Let's see. Yeah, so there should be a P mean and P standard deviation down there, if you can find it. Yeah, and that's the next task. Yeah, so I assume some of you already implemented DDPM already. You can take your time to implement it yourself, but I'm going to cheat a little bit here. So if you want to see the diffusion model training in effect, in action, you can just do a .gt here, highlighted here, and you can import everything from the correct implementation. Okay, so we can import everything. All right, so just visualizing the toy data that we're going to be training on. So it's a toy 2D distribution. And we're just going to put everything into the data loader and defining our noise prediction model, predictive model. It's going to be an MLP with some residual blocks. So it's not an MLP anymore. And the input is the noisy data and the time step and some other stuff that won't be used. And we simply just predict, since the 2D data, the dimensionality is just 2 at the end. Okay? And after that, we can instantiate the DDPM that we have. So right now, I'm using linear. You can also play with the cosine if you want. And you can, change the number of time step here. So remember the Q mean, the Q STD that you implemented by, indexing the alpha bar. You can increase the T here and see the effect of having more noise in the diffusion process. 50, it becomes noisier. Eventually, it's going to look like a Gaussian. And then you can start training. After training it for a while, you should be able to reproduce the same distribution you see here, which is a toy distribution. But I'm not patient. I can just terminate it right now and just visualize it. So this is the losses you see. It's decreasing, but it's going to be very noisy. And this will be the samples. It kind of looks like the toy distribution, but if you let it trend a bit longer, you can see it's going to look like the data distribution more. Yeah, you can play with the hyperparameters a little bit to see how it works.
Hello. Okay, so if you have already got this plot here, regardless or if you got it by your own code or with the ground truth, you can move to the next exercise, which is the QM9 dataset. So basically, we're gonna use this diffusion generative model for molecular data. Basically, now we don't have to change too many things. It's very simple because exactly the same diffusion model. The same diffusion model that we had before can now be used for this molecular data. So this point number 2, nothing has to be implemented. We can just run this one, and it's basically about the plotting, analyzing the data set. So I'm just going to run it on the screen, but you can also run it on your own laptops. So basically, what we're doing here is we're loading the training and validation partitions. So this is we call it a mini QM9 dataset. So we took the molecular dataset from the paper and we made it a bit smaller. Basically, it's like 19,000 samples for training, 3,400 for validation. Molecules are a bit smaller, maximum size of 15 atoms. If you run the next batch, then you will see that, well, here we just plot what are the shapes of a single sample. So, for example, the one that has been loaded here, it has like 15 atoms. Then we see X will be the 3D coordinates. So we have 15 atoms, 3D coordinates. 15 times 3. Then for the H1 hot atom type, we have, again, like 15 atoms. And then we have 5 possible atom types. Like carbon, hydrogen, nitrogen, oxygen, and I think the other was fluor. So that's why we have 5 here. Then the edge index, this is just the edges between the atoms. So basically, we're considering a fully connected message passing setting. So this is just like the edges that connect all the atoms. So this is like 15 squared minus 15. So it just defines the connectivity. Yeah, this is more for the neural network, so we really don't care so much. It's just we're going to pass it to the graph neural network to say exchange messages among all nodes. Then the context, we really don't care because this will be for the conditioning, so we are not conditioning here, but this will just be a property that we can condition on. And then batch, this is more just for, when dealing with the tensor for some operations. This basically tells, in case we have, for example, a batch size of like 2 molecules, it's going to tell which atom belongs to one molecule or the other. This is more like just a technicality on how the data is loaded, but it doesn't really have any meaning beyond just batching molecules. Okay, so yes, now that we have these data loaders, here's just a quick iteration, a quick for loop that does 5 iterations on the trained data set. Let me see this one. Yeah, so basically this just visualizes some of the molecules. So here you can see they take some time to render just because of the visualization tool, but we're basically visualizing five molecules. Depending on the angle, they may look a bit weird, but if the angle is good, then you can see maybe some of the shape, some of the rings that they form. Okay, so this will be just like the visualization of the molecules. And then the next one is a loop that just computes the atom stability. This is the metric that we computed in the paper for the validation partition. But this is computed on the ground truth data for this small data set that we have. Basically here we're just explaining what is the atom stability, how it is defined. This is what we explained before in the presentation. We say an atom is stable if the number of or if its valence matches the sum of the bonds. So for example, hydrogen is stable if it has 1 bond. This is a heuristic metric, so that's why it's not 100%, because actually molecules are more complex than just considering like pairs of bonds, but we get like, for example, an atom stability of almost 98% when checking the data set. We want to obtain something similar when training our model. Okay, and that will be the script number 2. So this is something that I see that some of you are already running. The point number 3 now is to train the diffusion model that we had. So basically, we just have to take the previous code and then we just have to add one mode change. So here in the right, we see how the loss is. Okay, so we see how the loss is computed. So basically, the main difference of the diffusion model now and the diffusion model before is that before we only had continuous data. We only had the continuous data of these 2 moons data set, and now we have continuous and discrete data. But as we mentioned before, the discrete data, we're treating it as continuous. So it's as basic as if you go to your DDPM, to the DDPM that you coded, there is one line here that says not implemented error in the method of the losses. So if you implement correctly the previous method, the only thing you need to change here is that now Z is not going to be just X as we have here, but in this, if H is not known, so we have an H, like the atom types, Z is just going to be the concatenation of X and H. So it's going to be the concatenation on the second dimension. This is basically the only thing that needs to be changed in the DPM model to go from the previous data set to the new one, just to consider this extra H component. So now, we can have like 5 minutes. People can try to code this and figure out if it works. In case someone didn't manage to do the previous session, actually this is again the same. Like here, models, like it's possible to just do like the ground truth and import the ground truth. I think this is already fixed in the ground truth. So if you do that, at least check how it is implemented to just see that that's the only difference that needs to be done. And after this, it's possible already to train the model and evaluate it for molecules. So let's just take some minutes. So you can change this function here like this if. Then you can already yourself try to run this thing. And then in few minutes, we will also show it in the screen. So then we can do it together. Okay, so we are going to wrap this up. So basically, I'm just going to go over the last part of the notebook. Then you don't have to do anything else. After this, we're just going to finish this lesson, but Rianne, Chin-Wei, and I, we're going to stay here for some question and answering. So if someone just has questions about anything, just feel free to stay. Otherwise, let's say the coding session will already be finished after I introduce this last part. So yes, basically in the last one, we have introduced the data, how the data is structured. And then we mentioned that the only thing that needs to be changed is in the DDPM, in the loss, that before we were passing this continuous value to the diffusion model. Now we are just concatenating the continuous and the discrete values. And then the same code that you used before for the toy experiment can be used for diffusion, exactly the same diffusion process. It's just a different data. So basically, if the code that you implemented before was correct, and then you added this concatenate, this should already work. Otherwise, we can use this trick of just adding the ground truth code here. And yeah, basically what we have is, we're just going to run the experiment that trains the diffusion model with the equivariant graph neural network with the diffusion model implemented by you in this file. So basically what we did now is we just initialized the data sets, the training and validation data loaders. Then we initialized the EGNN, this will be the EGNN network. And then we pass it to the DDPM module that we have been coding during this session. Once we have done that, we can just start the training. Basically, we can set like around 50 epochs. This will take, so we can get already some decent samples by training this for 50 epochs. This can train around like 20 minutes if we train for 50 epochs. Let's see here. Well, actually it says around 10 minutes, but we are gonna skip that. We're not that patient. We have already a checkpoint. So let's say that, we can load the checkpoint with this EGNN checkpoint. We just had a pre-saved checkpoint that was trained for, I think, 200 epochs. So it's still not too much. I think it was like 1 hour of training. But already produces some decent results. So we can just like load the checkpoint with this. And then we can use the DDPM model that we had to generate some samples. So here we're generating 128 samples. It just takes, it has to run over the 1,000 denoising time steps. It took 11 seconds, so it's not the fastest thing, but it also doesn't take that long. Then there is this thing during the presentation, I got this question on what about H? H is discrete, we get a continuous value. So basically that's what we're doing here. We are computing the argmax. So we get this one-hot representation, but it's continuous. We get some continuous values between 0 and 0.25 or 1. And then we want to compute what label, what atom it belongs to, and then we obtain the label by just computing the argmax. That's what we're doing here. And yes, finally, what we have here is just 2 scripts to compute the plots and to compute the molecule stability. So if we compute the molecular stability on the 128 samples, for example, in this case, we get an atom stability of 0.8. Molecular stability is 0 because it's for a model that's not been properly trained, we say a molecule is stable when all the atoms are stable. So as long as there is a single atom that's not stable, then the molecular stability is not. But at least empirically in the paper, we saw that around 80% to 100% is when the molecular stability starts increasing. And the paper, I think, by training for longer with a deeper network, we got like atom stability close to 90-something%, and then the molecular stability will also grow to 80-something%. And then, yes, we can just visualize the plots, the samples that we obtained. This has been done by this diffusion model that we have here, that trained for around 200 epochs instead of 50. And then we see that we can already start obtaining some realistic samples. This will be what we obtain. So just to compare, for example, if we will have so here we have some results on what it will be in case, for example, it was not working. So these are the, Sorry about that. Yeah, so basically, for example, these are the type of samples we're getting with this model. In case, for example, everything was Gaussian and noisy, it will be, we will obtain like these samples that don't really, well, this is basically just like samples in a Gaussian, in a normal distribution, and also the atom type also will follow, like it will be randomly assigned. Basically, when we train this model, then we start getting some structures, even we see some rings that are sometimes harder to achieve. And yes, this will be basically, the code that we needed for, to generate new molecules from scratch. Yes, so that will be all. I hope that this was useful, and you can also use the code for yourself, because this is something that we're publishing and sharing. So yes, that will be all. And then if there are any questions, we will be around here for the next 35 minutes, and then we're happy to have a chat. Thank you.